everyone. So this is the third and final question from the 2009-19 AP Physics C Mechanics question, set 2. Again, this is the rotation stuff. I always recommend try practice this yourself. The link to the question and the answer key are in the description below. So if we scroll down here, we have a scenario where we have this partially hollowed ball being placed down the ramp. It goes through the loop and it's going to probably fly off. They tell us that it's got some rotational inertia, which is some constant B, which is unknown and most likely something that we're going to look for later on. And they want us to figure out, well, for part A, they want us to figure out as the ball goes to here, it gets to A, and we want to know what is the minimum speed for the sphere's center of mass that will make it so that it doesn't lose contact with the track. That's pretty much the phrasing there. So the way we're going to do uh, this doesn't even require any rotational inertia. So one thing to note is if you look in this question, it says express your answers in terms of B, M, R, and fundamental constants. It's important to note that not every term is going to be used. In fact, a lot of times they throw in extra terms just to act as I guess you could say it's a red herring, but also so that you don't really know what stuff you should or shouldn't do, and to also make it consistent throughout. So if you also notice here, part B also uses B, M, and R. So just keep that in mind that sometimes you don't always have to use every single variable that they mention. But as we go through here, when it's going through this loop, I actually don't really need to worry about it being, having this rotational inertia. That doesn't really matter. They're talking about the speed of the center of mass. So what I'm going to do is to find the speed, the minimum speed, I'm going to look at the forces acting on the ball. At the top, there are two forces, the normal force and the force due to gravity. So F net equals ma is, of course, the equation I always start with. The net force is going to be mg, let's see, yeah, mg plus the normal. And this is going to be equal to this, because it's moving in a circle, it's going to be equal to m v squared over r, because that acceleration is the centripetal acceleration since it's a circle. Now, one of the key phrases here is the minimum speed for the ball sphere going here. That basically means that if we're looking for a minimum speed, this normal force goes to zero. Now, I know you might be thinking that it's saying without losing contact to the track, but that's because anything smaller than this speed will definitely let it big, uh, lose contact with the track. And even though there is no normal force, you could still consider this to be somewhat in contact, just not actually exerting a force onto it. So from here, I just solve this, drop the m's. V ends up being the square root of g times r. Actually, I need to be careful. The little r is being used as the radius for the sphere, and big R is the radius of the loop. So this is actually supposed to be mv squared over big R. So my velocity is going to be square root of g times r. This was a 2-point question. You got 1 point for this equation, and I guess for the substitution part. So this was worth 1 point, and then the other point was for this one. All right, so going down to the next part, it says, suppose that we leave it here and it goes down and rolls without slipping, yada, yada, yada. They want us to get this speed. So what is the minimum height to give us this minimum speed? So there's a few different ways I could go about doing this. I think the easiest, both of them are going to incorporate the same sort of setup. It's going to be conservation of energy. So what I'm going to do is at this height, it's got gravitational potential. And then over here, it's going to have gravitational potential plus kinetic translational plus kinetic rotational. So I'm going to do that. The energy is equal to energy initial energy equals final energy. So I'm going to call this the initial potential, and this is going to be equal to the final potential plus the translational kinetic plus rotational kinetic. So this is going to be mg h. This is going to be mg. Now this height, we actually do know what this height is. It's the diameter of the track, so that's going to be 2r, capital R. The translational kinetic energy at this point is going to be 1/2. I'm going to leave it as mv squared for a second. And then for the rotational, that's going to be 1/2 I omega squared. Right? So I can actually start trying to clean this up. Actually, I don't want to clean it up just yet. I want to actually clean up this part because one of the key phrases here is it rolls without slipping. Now, if you recall, one of the things that this tells me is that I can then say that if it's rolling without slipping, then this can be replaced and set equal to this speed, the center of mass speed. That's pretty much what it's referring to. So what I'm going to do is I'm going to put that in. So 2g, 2mgr plus 1/2 mvc squared. That's this term, vc for center of mass, plus 1/2. So omega is going to be equal to that center of mass speed divided by its radius, like its radius. Oh, and I've just remembered that they told me that I was equal to this, so I can plug in b m r squared divided by vc over r squared. This is actually going to help cancel out a lot of things. For example, there's now an m in each term. There is also an r squared here. That cancels out with that. So now this becomes gh over 2gr plus 1/2 vc squared plus 1/2 bvc squared. Let's see what else I can try to clean up. I can divide the g over. So this is going to end up being, we'll say 2r plus, I'm going to be able to pull out a 1/2 vc squared from all the terms. So it's going to be vc squared divided by 2g, because remember I divided g, like the whole thing, by g. And this is going to be multiplied by 1 plus b. Let's see. I think this is pretty much as far as I'm going to be able to take it. Oh, right. Actually, no, I can take it a step further. I know what VC is. I'm looking over here. I notice that VC is not a given term. So let me keep this momentum going. So VC squared is just this without the square root. So this is just going to be GR over 2. G's drop out. 1 plus B. So now I have 2r plus r over 2 times by this. I'm actually going to, just to make my life a little bit easier, I'm going to actually redistribute that term. Oh wait, where'd the r go? R. And then this will be b times r over 2. So I can actually start cleaning this up. I can pull an r out from this entire thing. Actually, I'm going to pull out a 1/2 r from this entire thing. So this 2 becomes a 4. So everything's going to get doubled. The half goes away. So that just becomes 1. The half here goes away. So that's just left with b. So then I end up with h equals 1/2 r 5 plus b. So it's really messy. And you'll notice that we don't have the m anymore. It's all in terms of b and r. This was a 3-point question, so you got 1 point just for pretty much stating this line. 1 point for pretty much all of this work. So this was 1 point. And then you got 1 point for, where is it? All this work, where you took your speed from before, brought it down here, and then you got a height that pretty much made sense to that. All right. So let's see. The next part, they end up doing the experiment. They get a bunch of different minimum heights and the different b values. They want us to plot this as height versus b. I mean, that doesn't really require too much effort. Let's see. Height as a function of b. So my height's going to be here. B is going to be here. Height goes to 1.2. So what I'm going to do is every one of these lines is 0.3. That should, yeah, that should do it. 0.3, 0.6, 0.9, and 1.2, because my max height is 1.2. This has to go up to 1, so that should be pretty easy. 1, 0.5, 0.25, 0.75. Let's see, now we have to plot the points. So let's actually make this a little bit bigger. 0.4 and 1.08. So 0.4 is going to happen pretty much right here. And then I'm going to go up to 1.08, which happens at right about 10, 15, right here. So that's going to be 1 point. You know what? This one's actually easy. 1.2 and that. Let's see. 0.67 and 1.13. So that's going to be 0.67 is going to be right about here, right here, and this is going to be right there. You know what? I think I'd actually want to change up how I did this graph. So, because I actually want to be able to see everything a little bit clearer, instead of starting from 0, my lowest number is 1. So I actually want this to start at 1. And then from here, I'm going to do 1.05, 1.1, 1.15. Alright, this is going to make the line a little bit nicer. So this first point, which is 1.08, is going to be 0.05, 6, 7, 8 right there. The next one, which is 1. Well, we already have this point right there. I can actually do this one easily, 0.5 and 1.1. And then the last one, 0.67, which is, we already said was about here. Going to go up to 1.13. 1, 2, 3. There we go. So those are my lines. Doing the line of best fit. It's going to look like that. Your graph doesn't need to go to 0. So let's see. Was that all I had to do? Yeah, draw a straight line. Okay. So looking at the answer key, there are 4 points for this. All right. So I actually didn't get the full point for this. I was completely not really focused. This should have been in meters. So I actually would have lost the point for not having the unit there. But you get 1 point for labeling your axes, H and B, in their proper spots and making sure that H has units. Besides that, you end up getting 1 point for the labeling, essentially, and making sure that you fill up the graph. So thankfully, I did change it at the last second. The graph that I made would have only been focused up here and would not have been enough. Plotting the data gets you that 3rd point, and then drawing this line of best fit gets you the 4th point. So this one actually was fairly easy to get the points. Like I said, I made a simple mistake only because I'm just so focused on trying to graph this properly. All right, going to part D. Let's see. The students repeat this with the partially hollowed sphere. Determine the minimum release height to be 1.16. And they want us to figure out what this B value is. So the best way to do it, now you might think that the best thing to do is to go onto this line and pretty much just read it from your line of best fit. Unfortunately, they will not give you credit for this. They want calculations. They want work for this. So let's see. Just for the fun of it, though, 1.16 would have been right here. So according to my calculation, it B should be about 0.8. Let's see if that's accurate. So what I'm going to do is I'm going to do slope. Let's see. Let's pick 2 points. Okay, I'll use these 2 points. They cross my line fairly close. So let's see. Slope. Let's change in y over change in x. My y values are 1.15 minus 1.05. X values are easy. They're 0.75 and 0.25. So when I do this, I get 0.1 over 0.5. So it's really just 1 over 5. So this ends up being 0.2 for my slope. I guess meters would be the slope. Then what I can do is essentially realize that this is y equals mx, that this is going to be h equals slope times b. So since my height was 1.16 equals 0.2 times b, basically divide the 1.16 by 0.2, and I end up getting 0.96 as my answer for B. Um, oh, right. here's the mistake that I made. Uh, because of the fact that this isn't starting at 0, I completely forgot that this has to start with some y-intercept, and in this case my y-intercept is 1. So I actually had to subtract the 1 over first. Let's actually delete this. So this ends up being 0.16 divided by 0.2. So 1.6 divided by 2 gets me about 0.8. Didn't make sense with what I got here. So that's kind of how I realized that this was not accurate at all. But you'll notice that I would have gotten the answer had I just read the graph. But again, that's not what they're looking for. They want you to actually do the calculation. So you're not really allowed to just go the simple route. As much as you are going to be wanting to do it, avoid that. Always, if they're telling you to use a graph, you want to start figuring out how to use slope. So this was a 2-point question. All it really was 1 point for, I guess, doing all this part, taking the slope and then realizing that you had to set that equal to the equation for a line. And then 1 point was for this answer of 0.8. All right. Let's see. Part E. Let's see. Part E. Calculate the radius of the loop. So if we go back to here, I actually already know how to figure this out. They want the radius of the loop. So what I can say is I could pull back this equation, 1/2 r 5 plus b. I can plug my numbers in. So this is 1.16 equals 1/2 r times 5 plus 0.8. So this ends up being, we'll multiply that, so that'd be 2.32 equals 5.8 r. So 2.32 divided by 5.8 is 0.4. Easy enough. Okay, so let's see. Part F. Oh, right. This is a 2-point question before I continue. This is a 2-point question. You got 1 point for all of this work, and then 1 point for this. All right, part F, the last part. They said that the radius that we ended up using is was much smaller than the radius of the loop, and they want us to figure out about how if the radius of the rolling sphere wasn't negligible. So if we go back up to here, they wanted to figure out the, let's see if it was in part B. All right, they wanted to see how this answer would change if the object's radius was, I guess, much larger relative to the entire loop's radius. So you can go about doing this conceptually. Let's actually use the equation. So actually, I'm going to draw it out. So we have the loop, goes here and it comes up like that. So what pretty much ends up happening is that the difference, this height that they end up getting, and this distance is going to the center of the object because that's where all the mass is. Uh, it's not going to be 2r anymore. So let's see. It would be, this would still be mgh. This, on the other hand, would be mg. It would be the diameter of the entire loop minus this little radius part. So this would be r minus, oh, sorry, 2 big R minus the little r. And then plus, all this stuff. So what they're saying is if this is negligible, like if this r is really, really tiny, I could just ignore it. But as this increases, then this entire term, this energy term, ends up decreasing. So because this ends up decreasing, well, the right hand side of the equation ends up decreasing. That means this side has to also decrease, which means that h would have to be less. This this could be explained a variety of different ways. This could be mentioned that that the center of mass of the object doesn't go as high as it did originally. Originally we assumed that the center of mass was essentially right at where A is, but it's actually going to be a lot less than that. So yeah, that's pretty much it. So I'm trying to think if there's any other. Sorry for the delay. I'm trying to think if there's any other way to explain it. I don't really think so. I think that's probably the easiest mention is the fact that the center of mass is no longer at the edge of the loop, but is now a little bit further down. So the final height is lower, which means that the entire energy at the end is has gone down, which means the energy in the beginning has to be a little bit less. Um, Basically, that's it. Do you have any questions? Oh, actually, before I say that, there's this one was 2 points. 1 point for saying the word less, and 1 point for some sort of explanation. I don't think you have to put it directly into words, but you could just explain that. Like once you do, this, you could explain what it's meaning in words, kind of like what I did. Of, as this goes up, the potential energy at the end goes down. Blah blah blah. So that's pretty much it. If you have any questions, feel free to let me know. Otherwise, good luck and have a great day.